Okay, so hi everyone. So as I promised, today I'm going to do this Lagrange multipliers. That's a technique that we need for maximizing and minimizing techniques. So today is Lagrange multipliers. So the kind of typical problem for this sort of situation that you might have is, so here's a kind of typical problem that you may encounter in life, actually. Imagine you want to solve this problem, say, minimize the function. Minimize the function f of x and y equal to x2 minus y2, subject to the constraint, subject to the constraint. Well, the constraint is kind of not really technical, but it's a word that's used in this business. It means condition, really. It means the limitations for your problems. You are not free when you see constraints. Subject to the constraint. So what is the constraint in this case? X plus y plus 6 equal to 0. X plus y plus 6 equal to 0. Okay. So what does this problem mean? So if we just have this function, f of x and y equal to x2 minus y2, if we had this problem without constraint, right? So solution without constraint. So imagine we didn't have this extra condition, like we were like in usual stuff that we have been doing so far, without any constraint. Then it means that x and y are completely free because no other condition is given. So you're allowed to change x and y over all of R2, right? So in that case, x and y is going to be everywhere here. And then in that case, can you tell me what would be the minimum of this function? F of x and y equal to x2 minus y2. Sorry? So, okay, yeah, what does that mean, no minimum? There's an answer also. Negative inf. There's one answer, negative inf. Maybe that's what you meant also? Negative inf also? Yeah. I think that's indeed. If there's no condition, this function can take smaller and smaller values as you wish. There is no restrictions for this function. Why? So minimum, in this case is equal to negative infinity. Why? So without constraint, minimum would be negative infinity. Why? Can you tell me why? You could take, for example, the answer would be, you could take x equal to 0 and y to be bigger numbers. In that case, it would go to minus infinity, right? Just let x equal to 0. So on this line, in other words, if you stick yourself to this, just this line, y-axis, which means x is equal to 0, and y arbitrary. So then this function, as you move up or move down, this function is going to minus infinity, for sure. So If you don't have any constraint, the problem has no minimum and also no maximum, right? And no max. So again, if you tell me no max, I would ask you what you mean by no max. Then you would say, well, the maximum in some sense is infinite because it takes larger and larger values. In fact, infinity. Why? In that case, obviously, we have to restrict ourselves to the line x arbitrary, y equal to 0. So on this line, the function goes to plus infinity. On this line, the function is goes to minus infinity. And of course, on the line y equal to x, full function is just 0, right? And on these two lines are also 0. But it doesn't matter. We just want to study max and mean in this problem. Okay, so that's the easy problem that we already know how to solve, and we already tackled this sort of issues before. But here is something new. Look, we are told that x and y are not arbitrary. X and y are subject to this condition. What is this condition, x plus y equal to x plus y plus 6 equal to 0? Well, the condition is that x plus y is equal to -6. So if you want to draw it, this is going to be -6 here, this is -6 here, and you just draw this line. And that's the line. That's the line x plus y plus 6 equal to 0, right? So now we are told that, no, you cannot be anywhere you wish. You have to be on this line. That's the constraint, right? So this is the constraint then. And now we are asked if we can find the maximum and minimum possibly of this function if x and y are confined to this line. X plus y plus 6. You see that this is a totally different problem. This is not like the original problem. Our original problem was easy because there was no constraint and we know how to tackle those questions. But here we are constrained, confined to this line. So we have to come up with some method. This problem actually turns out to be not too difficult. You don't need a new method for this problem because you can just easily solve for x or y in terms of the other, and go back to your original equation. You get the function of x or y, and that function is x or y, just one variable. That's a free variable. You can maximize, minimize it, and that's not a problem. But the point of Lagrange multipliers is that that method is not always available. You cannot always solve, this is an easy case, you cannot always solve this equation so easily. So we have to come up with a new method, and that's what Lagrange did in already around 1780s, I guess. So, and it's such a great thing. Still, we are talking about Lagrange multipliers. It's amazing. You do one good thing, and then people remember you forever. That's incredible. But there are many things named after Lagrange. If you study physics and mathematics, you see that he's one of the greatest names. So let me tell you now the general idea, and then we go back to this problem. This was just a warm-up. Before solving this problem, we just get the general idea now. So general idea is this. So we have a function we want to maximize or minimize, f of x and y. So want to maximize or minimize. I would say extremize. But then there is a constraint which is in terms of another equation, which would be of the form. Yes, okay, so which is of the form g of xy equal to 0. Okay, so this other equation is, so we have two things, g of xy equal to 0. So that's our constraint. So geometrically, when you think of g of xy equal to 0, you're thinking of one of these curves in general. Of course, in this case, because it was a linear equation, it was easy. So, but in general, it could be very complicated curve. I mean, so it could be anything. It could be very complicated. So this is g of xy equal to 0. So that's your universe now. You're not allowed to be everywhere on R2. Someone says that, well, you have to be here. Find the maximum minimum function if x and y are just confined to this point. That's your universe. Okay. Could be. I mean, this could be a curve of something. You know, this could happen. Okay, so how would you untangle this kind of mess? I mean, we cannot just take partial derivatives of f. Fermat's result, it does not apply, because for that, we have to be on an open neighborhood of a point, a maximum minimum point, in order to do that. And that's where Lagrange comes in. And so let's see how we tackle this problem. So, so the result is in the following form. So assume at the extremum point, this is a condition that we always assume is true, or holds, in other words. Assume at the extremum point x0, y0, so f of x0, y0 equal to 0, oh, g of x0, y0 equal to 0. We have gradient of this function g is different from 0. Gradient of g, which is gx, gy. Now at this point, x0, y0 is different from 0. So it means that one of these partial derivatives at this is not 0. It's not that both of them are 0. That's the case that we don't want to have, because things could go wrong. So let's assume this. That's an important assumption. Then there exists a number or parameter lambda so this is called Lagrange multipliers. Such that now we have these two equations satisfied. The first equation is that gradient of f is a multiple of gradient of g, such that at x0, y0, we have gradient of f equal to lambda times gradient of g. And of course, g of x0, y0 is equal to 0. Remember, I mean, this second condition, of course, has to be satisfied, because we are saying that we want to be on the constraint. So my constraint is here, so I want to be here. So we are looking for some function, some points here, right? And this has. Now, you can write this equation. In fact, the first equation, how many equations are here in the first one? How many equations are kind of hidden here? Two equations, because it's a gradient of a function of two variables, so it's a vector equation, so it has two ingredients. So I can write it in a different form now as a result, which is of this form, f sub x equal to lambda g sub x, f sub y equal to lambda g sub y, and g of xy equal to 0. I mean, I could have put here, but without that also, it doesn't matter. You see, now we have 3 equations, 3 unknowns. And there is no constraint here except that it has to be satisfied this equation. So if you allow yourself to get a bit more complicated than just solving gradient of f equal to 0, no, you want to solve gradient of f equal to lambda times gradient of g. So this looks quite a trick. I mean, and you don't know why this is true actually and why it should work. I will prove this theorem that I just raised here. It's not difficult. Well, I mean, we have everything that we need in order to prove this, basically. But let's first learn how to use this. And then I will give you an idea of the theorem. Because this by itself is kind of, now we have a more difficult task. We have 3 equations, 3 unknowns. Any questions? So far, no? Okay, very good. So now let's go back to solve our problem. So we had, remember, f of x and y equal to x2 minus y2 for our original problem. And g of x and y was x plus y plus 6, right? So this was constraint. And this is our function we want to. Okay, so let's see if we can now solve this problem using this condition. Right? Okay, so the equations then are fx. What is fx? Fx is equal to 2x. Has to be lambda times gx, which is just 1. So this is really 2x is equal to 1. Right? So that's, oh no, equal to lambda, sorry. Yeah. Look, fx equal to lambda gx means, so this is not very good, sorry. Fx equal to lambda gx means, terrible writing there, just means that indeed 2x is equal to lambda, because just compute gx is 1, lambda times 1 is lambda, as this is. Now, fy equal to lambda gy means, now fy is negative to y, it should be equal to, but gy is 1 again, so it's lambda. And of course, the condition is x plus y plus 6 equal to 0. Okay? So now, typically what happens in Lagrange equations, multiplier equations like this, is that usually we end up finding lambda first, and then we find x and y. It's not the other way around. Sometimes you may find, but usually we find lambda first. And in fact, in this case, you see 2x is equal to lambda, negative 2y is equal to lambda. So we just take these values, substitute into this, and we find the value of lambda. So here we get x equal to lambda over 2. Here we get y equal to minus lambda over 2. And from this equation, we have got what? Awful. Lambda over 2. What did I do? Lambda over 2. Minus lambda over 2 plus 6 equal to 0. So there is no lambda. All this cancels. 6 cannot be. So did I look at it right? Yes. 2x equal to lambda. Negative 2y equal to lambda. Lambda gy, yes. and x plus y plus 6 is equal to 0. So we get yes. So I got that. Okay. So there is no lambda. So no solutions. What does that mean? We didn't find any solution. Is it the end of the world? Are we proving that, I don't know, God does not exist or exists or something like that? No, right? There's no, I mean, I'm saying, is there a contradiction here or not? Yes? Why?
6 doesn't equal 0.
Sorry?
6 doesn't equal 0. So it's a contradiction.
Did we derive a contradiction? But then we are in a very bad situation. Either we made a mistake or we have made something really big because we derive a contradiction in mathematics. We proved 6 is equal to 0. If you prove 6 is equal to 0, then nothing stays. I mean, the whole world will collapse, I can tell you. But did we really prove that?
Did we just show that there's no lambda?
Yeah, exactly. You see, those kind of conditions were conditioned on one thing, that there exists an extremum point. The result said if there is an extremum point, then at that point, these equations are satisfied. There is a lambda, We are not going backward. Nobody said that the backward is also true. You see, you see that the logic is only one way. The logic of the theorem was that if there is a condition, if there is an extremum point, then at that extremum point. So there was another condition at the extremum point, by the way, also. What was the other condition at the extremum point? That the gradient of the function has to be non-zero. But the gradient of this g is, of course, it's non-zero. It's just 1, 1. Full function is just 1, 1. So there's no way that gradient could be. So that's satisfied. So now max or min points. Min points. And that's very valuable to know, min points on the line. X plus y plus 6 equal to 0. If we didn't make any mistakes, that should be our conclusion. Okay? Good. So, but now let's go to a question that has some positive answer at least. So that this was a kind of bad start in a way. So, but, well, that's actually, I mean, I actually think it's a good start because it exactly gave you a kind of a shot that you need kind of to see this sort of issues. Any questions about this? Okay, so let's look at another question. So example is minimize the function of x, y, z. Now you have 3 variables equal to x2 plus y2 plus z2 subject to constraints. Yes. X plus y plus z equal to 9. And x plus 2y plus 3z equal to 20. So notice now Can you read? Notice now there are two differences in this problem, right? All of a sudden now we have moved to 3 variable functions. That doesn't matter much because we just continue, because gradient, we can do gradient in 3 variables, 4 variables, n variables, that's okay. And but the other thing is that we don't have one constraint. Now we have 2 constraints. Now, I did not discuss when situations where we have 2 constraints. What should we do if there are 2 constraints? I did not discuss those situations yet, right? So it means that there is room to discuss also maximize, minimize, extremizing functions subject to 2 constraints, 3 constraints, things like that, right? So before telling you about that, let me just give you the geometric meaning of this problem. What's the geometry of this problem? What is it that we are asked to do here? It's very important to know that, right? What this question is asking, in a way. So we have this condition or constraint x plus y plus z equal to 9, right? So this just defines what? What kind of object is this in 3D space?
A plane.
It's a plane, exactly. It's a plane. And we have a very good idea, actually, of the shape of this plane, because x plus y plus z equal to 9, well, you just go in the negative direction. Go minus, so if this is x, this is y, this is z, this is negative x, go negative direction by minus 9, go negative direction by minus 9, come down by negative direction minus 9, and then connect these things. So that's exactly the portion of the surface that is in this part, but really the surface, of course, goes all the way to infinity. But I mean, don't think that this is just a part of it. It's just a surface, it's just a plane. Now, what about this guy? X plus 2y plus 3z equal to 20. This is also a plane. So this is a plane. This is also a plane. Okay. So what now this plane is, we are here now. So it's okay. So just draw that. It's not symmetric because these numbers are different now. Here the numbers are the same, so I could easily, but here they are not symmetric, so you just find the corresponding numbers here, and then, okay, so this is the portion of the plane, second plane, and this is the portion of the first plane, right? Now, you want to be here and here both. What does that mean? You want to be in the first plane and you want to be in the second plane. Well, you have to be in the intersection of the two. So you are on the line then, right? So there is these 2 planes intersecting. And they're intersecting on this line. So all we're saying is that we are on this line. So this line is somewhere, we don't care so much for the line. But now what we are asking to minimize this function, f of xy equal to x squared plus y squared plus z squared. What is that function? X squared plus y squared plus z squared. That is square of the distance to the origin, right? So in other words, what this question is asking is, find a point on the line which is closest to the origin. That's what this question is asking. It's a very, very geometric question. Of course, it would be a square root if it was exactly the distance, but that doesn't matter. If you maximize or minimize square root, then you have maximize or minimize the function itself. Because if you squaring, you get the same square values, but point is the same, right? Okay, so then that's good. So we have here, so we have to find a point on this line somewhere in the space that's closest to the origin. So smallest distance. to origin. Okay, so that's as far as geometry of the problem goes. Now, but nevertheless, how do we solve this question? There are two constraints. And for these two constraints, there are similar equations. So in this case, so let me write it down then. We'll erase this and then we'll write it again. That's okay. So this is two constraint Lagrange multiplier problems. So in this case, it says that there are two numbers, lambda and mu. So there exists two numbers, lambda and mu, such that gradient of f is equal to lambda gradient of g1 plus mu gradient of g2, of g1 and g2 are constraints, and g1 xyz equal to 0, g2 xyz equal to 0. How many equations, how many unknowns we have here now? Let's do a count. How many equations are here, hidden in the first one? 3 equations, because it's a gradient of a 3-variable function. So there are 3 equations here, and we have 2 equations here, so we have 5 equations. Okay, so 5 equations. How many unknowns we have? Well, what are the unknowns? Unknowns are x, y, z, and lambda and mu, and 5 unknowns. Unknowns lambda, x, y, z. Lambda, mu. So there are 5. Okay, so at least the count is good because we have as many equations as unknowns and there's a chance to be able to solve those. Okay. So this is also part of the things you have to remember and you have to be able to use. So this is obviously more complicated, and but with kind of diligence and practice, there are many questions in your text. You can learn how to handle these problems. So let's go back now to our original question and solve that. The second question with 2 constraints using this one. So back to our original problem. Well, f of x, y, z was x2 plus y2 plus z2. So this means that gradient of f, which is fx, y, z, right? Well, this turns out to be equal to 2x, 2y, 2z, right? That's equal to 2x, 2y, 2z. Now, G1 was x plus y plus z plus 9 equal to 0, was it? Sorry? Oh, minus 9. Minus 9 equal to 0. Thank you. And G2 was x plus 2y plus 3z minus 20. What did I do for the first one? Oh, the picture I drew was not correct. I drew x plus y plus z. No, it's minus 9, not 9, but that's okay. So this is like x plus 2y plus 3z minus 20. X plus 2y negative 3z negative 20 equal to 0. So here we can find gradient of G1, which is equal to 1, 1, 1, and gradient of G2, which is equal to 1, 2, negative 3, right? So the equations that we are solving is the following: 2x, 2y, 2z equal to lambda times 1, 1, 1 plus mu times 1, 2, negative 3. That's one equation. And I mean, these are three equations, really. And the first fourth equation is x plus y plus z minus 9 equal to 0. And fifth equation is x plus 2y negative 3z negative 20 equal to 0. Cool. So now, this first equation tells us something, right? The first equation tells us, so let's continue here. So 1 is telling me that, well, 2x is equal to lambda plus mu. And then 2y is equal to lambda plus 2 mu. And 2z is equal to lambda minus 3 mu. 3 mu. And now what we have to do, we have to sum in these three values into these two equations, and then we get two equations and two unknowns. So that's nice, right? So in these into last two equations. So these last two equations are these ones. So I've got x plus y plus z minus 9 equal to 0, where x is equal to lambda plus mu over 2. And y is lambda plus 2 mu over 2. And z is lambda negative 3 mu over 2 minus 9, or equal to 9, actually. And the second equation is x plus 2y, so lambda plus mu over 2 plus 2y. 2y is lambda plus 2 mu. And the last equation is negative 3z. Is that correct, negative 3z? How come this turns out to be negative 3z? This is positive 3z. Oh no. I made a mistake here. This is positive 3z. I'm sorry. I don't want to. But that doesn't matter. You can just conveniently change this thing just to be, yes. Just switch the minus. Okay. Lambda plus 2 mu plus 3z plus 3z. So 3 times lambda negative 3 mu over 2. Yes, that's good. Over 2. Lambda negative 3 mu over 2 equal to 20. So now look, you have got two equations, two unknowns. So you stand a chance to solve this. Two equations, two unknowns. Good. So let's go after the solution of this and then see what we find. Any questions? Okay, so let's continue here. Okay, so we can multiply through by 2 and then add, so we get lambda, lambda, lambda is 3 lambda. And then mu, 2 mu is 3, negative 3 mu is 0, so lambda is equal to, 3 lambda is equal to, well, that's a very nice equation, equal to 18. The first equation tells me that lambda is equal to 6. Now, what about the second equation? Multiply through by 2 again. We get lambda, lambda, 3 lambda. I've got 2 lambda, oh no, lambda, 2 lambda. And then 3 lambda, I get 7 lambda. And now mu plus 4 mu, which is 5 mu, and negative 9 mu, 5 mu, negative 9 mu, negative 4 mu. Negative 4 mu is equal to 40. Yes. You have to speak louder.
Wasn't the sign in like the second constraint? Didn't you change that back to positive?
Sorry?
The sign in the second constraint, so x plus 2y plus 3z.
Yes.
Or is it minus?
Or it's plus 3. Oh, did I use negative? Oh yeah, that's a good point. So I forgot to change here. Yeah, that's what you meant, right? Yeah. Okay. So now, okay, so that makes the equation that is a bit more interesting. Thank you. So I just get the equation now. I've got what? Like 3 lambda. Mu's now don't cancel. And then I get plus 6 mu, right? Equal to 18. And what about this one? Does it change? The second one does not change. Does it change?
Yeah, I think so.
Sorry?
I think it does.
Why?
Because you changed it to plus 3 mu.
Sorry?
You changed it to plus 3 mu at the end in the second equation, the last term.
Okay, so let's see. Oh no, I changed. Yeah, I changed it, and then I looked at it. I thought this was before change like this. Yeah. Okay. So very good. So what we get? What we've got here? So this is lambda, 2 lambda, 3 lambda. I've got 2 lambda, lambda, 3 lambda. This is 6 lambda. I've got 6 lambda now. Lambda 2 lambda is 6. So I get 6 lambda. I mean that 7 was mistake. And what about mu's here? So we've got mu, 4 mu, which is 5 mu. And then here is 9 mu, which is 14 mu. My God, yeah, this is high school stuff that's torturing me. So that's okay. So now you can solve 2 equations, 2 unknowns. Please solve these equations. So, well, let me just do it. Multiply this by 2 and subtract. You get 12 minus 14 mu equal to 36 minus 40. So we've got negative 2 mu equal to 36 minus 40 is what? Minus 4, I believe. So mu is equal to 2. And you sub into this equation, you get 3 lambda equal to 18 minus 12, which is cool, 6, lambda is equal to 2. Okay, so we found the values of lambda and mu. So, but what? So what? We were looking for a point on these two lines, on these two planes, that has the minimum distance to the origin. So what is that point now? Well, we have to use lambda and mu equal to 2, 2, sum into the original equations and get the values of x, y, z. So that's an important point. So now these equations tell me that. So you have to go to drawing board again, so to speak. So here we have now x is equal to lambda plus mu over 2. But we found those values is 2 plus 2. That's equal to 2, so that's nice. And here we have y is equal to lambda plus 2 mu over 2. Well, lambda is 2 plus 4 over 2, which is 3. And finally, this one gives me z is equal to lambda negative 3 mu. I hope this is okay. It was a comment.
Isn't it plus 3?
Oh, yeah. I trust you. I don't want to think about it anymore because it tortures me now. Over 2. So that's equal to lambda, which is 2, 6, 8 over 2, which is 4. So we have got this, so there's a unique point. So there is just one point, which is, by the way, this point of 2, 3, 4. This is closest to the origin. And we can actually, so I think we made good progress today because we discussed both cases of Lagrange multipliers in one Lagrange multiplier and 2 Lagrange multipliers. So this was a good thing. And we did several examples, some geometry. So this was very good. I'm glad that it turned out good. Thank you very much. And thanks for your contributions. It's very good. Any questions from the home audience? Okay, guys, so have a wonderful day. I just stop and then I'll see you.